Good day, ladies and gentlemen. You are welcome to our lecture number 3 on CMEN 407, that is Introduction to Semiconductors Microelectronics. And in this lecture, we'll first start looking at the postulates of the quantum mechanics. If you can remember, in our lecture number 2, we define quantum mechanics as a collection of postulates. So today we look at this postulate. It depends on the authors. Some will give you 1 to 4, some will give you 1 to 5, some 6, and maximum I came across, and of course in the literature, is 7. So let us start looking at these postulates one after the other briefly. The postulate number 1 says every physically reliable state of a system is described in quantum mechanics by a state function psi. This is psi, and it is the state function that contains all the accessible physical information about the system in that state. So what is this postulate trying to tell us? It is saying that if you have any state which is physically realizable, and if you say physically realizable state, what you mean is that that state can be studied in laboratory. So any state that can be studied in laboratory can be defined by this state function psi, and it contains all the accessible physical information about that system. What is accessible physical information? The information that we can extract from the wave function psi is what we call the accessible information. And finally, we set a state function. What is a state function? It's a function of position, function of momentum, and function of energy, which are spatially localized, meaning they are located at different spaces. Any function that takes care of position, momentum, energy is what we call a state function. So this is the postulate of quantum mechanics. So for us to get more information about this postulate, let us assume these psi 1 and 2 are physically realizable states of a system. Then you can have a third state psi, which is C1 psi 1 plus C2 psi 2, where this psi 1 and psi 2, they are arbitrary complex constants. They are constant values, but they are in complex form, not in real form. And this psi represents the third state, which can be obtained from the combination of the two first realizable states, that is state psi 1 and psi 2. And this function is a function of position and time. And of course, we have said in our lecture number 2 that everything about quantum mechanics is probabilistic. Therefore, this function is a function of a position and time, which are probability amplitude, meaning the amplitude you can get for the time and the position, they are not deterministic. They are probabilistic, which means they are by chance, they can change. So the second postulate of quantum mechanics says if a system in a quantum state represented by a wave function psi, then P dV is equal to psi absolute value square dV. What this is saying is that this P stands for the probability that you can measure the position, or you can measure the position at a particular time. That is the meaning of P, the probability of measurement of a position of a particle at a particular time. It is the probability that that particle can be detected, that is, can be located in infinitesimal volume dV. That is, in a very small volume, you can determine the position of a particle in the space, and P stands for the probability dV is that small volume. So how do you get that probability? Is the square of the absolute value of the function psi. And we have already mentioned previously that this psi is always a function of position and time. Therefore, the square we are going to take here is the position and time probability density function. So according to this second postulate of quantum mechanics, the integrated probability density can be interpreted as the probability that in a certain position in a measurement and at a particular time we can locate a particle anywhere that's within that small space, that is infinitesimal volume. It is telling us that whenever you want to detect a particle in a field of quantum mechanics at a particular time, you have a probability of getting that measurement. And of course, everybody knows that the probability ranges from 0 to 1. If it is 0, it means finally the probability does not succeed and you didn't get it. When you get 1, then 100% accuracy, which is not actually always possible. So this is the repetition of the formula we have just seen. Therefore, if you normalize this equation, you have to take the integral of both sides. That is, the integral of PDV is equal to the integral of absolute value of this psi square. But this time around, in normalization, we have to take care of all the three dimensions. That is x-axis, y-axis, and the z-axis. And if you do that normalization, you end up getting this your psi prime. Instead of taking square, these coordinates xy axis, xyz axis are multiplied twice to take care of the square, and it is telling us that the probability finally must be equal to 1. That is, if you take the integral over the whole region from minus infinity to plus infinity. So this wave function has some limitations. Limitation number 1 is only normalizable functions can represent a quantum state, and these are called physically admissible functions. That is, any function that is given for you to be able to determine the probability of locating a particle in a space. If you cannot normalize it, that is, if you cannot modify it to take care of all the three coordinates x, y, and z, that function cannot be used for determining this probability. The limitation number 2 is that the state function must be continuous and must be a single valued function. If you can remember your limits in differentiation, maths 105 in 100 level, we do determine whether the function is continuous or is discontinuous at a particular time. So we are now saying that even if you can normalize the function, it has to be continuous function and it must have a single value at taking limits 10 to 0 and taking direct substitution, if you can remember your continuity analysis. So the function must be continuous and it must be a single valued. Then the limitation number 3 is that the state function must be smoothly varying function. That is, it must have a continuous derivative. What we mean by continuous derivative, it means it is a function that if you directly differentiate it, it will give you value. If you take limit analysis, it will also give you value. So we call it continuous derivative function. So if we go to postulate number 3, the postulate is saying every observable in quantum mechanics is represented by operator. Anything that can be observed in laboratory by experimental methods, we have to represent it by an operator. And this operator is used to obtain the physical information about that observable from the function. And for us to understand this better, let us assume we have an observable which is represented by a function q of x comma p, where x is the position and p is the momentum. So the corresponding operator of this function should be q. Instead of x, we have x bar, and instead of p, we should have what? P bar. So here is a table that gives us comparison between the three major components of our observables: position, momentum, and energy. The operator for the position is x bar. We know x is the position, so x bar is its operator. And the momentum, as you can remember, is equal to h over lambda, and that h over lambda is equivalent to h over I d dx, that is partial differentiation of this I, where this I is any initial value for that wavelength. And the energy, as you know, the kinetic energy, we can express it as p square over 2m, but this time around you have to add it to a constant value v of x, which is also an energy existing in addition to the kinetic energy, and you can express it as second order derivative of this function in partial terms. So this table gives us three major observables and their corresponding operators according to the quantum postulate number 3. Now, if we want to give more information about these operators, we look at operator as an instruction or as a symbol which is telling us what to perform. That is, we have to perform some operations, one or more mathematical operations on existing function. For instance, if you are given f of x, so f of x bar, it means we have taken one operation of mathematics, either integration, differentiation, depending on what we want to obtain. And the essential actions that can be done, they are constrained by brackets. And the first one is we can carry out addition or subtraction, which is a mathematical function. You see, let us assume we have a function q1 bar is an operator plus or minus q2 bar. So the operation that can be taken on this is q1 times f of x plus or minus q2 times f of x, meaning each one of these operators has taken its own function f of x in terms of addition. And the next one, you can carry out a product operation on two operators. If you have two operators, for instance, you have q1 bar times q2 bar f of x. So the operation you can carry out on this is to leave the operator number 1, q1 bar, outside, and then you have your q2 bar multiplied by this f of x. That is the product operation we can carry out on two operators. And the product of two operators is always a third operator. That is, if you multiply operator q1 bar by q2 bar, it will give you q3 bar, which is a third operation. And finally, whenever you have two operators, they must commute. What we mean by this, they must be commutative in nature if they obey the simple operator expression. What do you mean by commutative law? Supposing I have q1, q2 all in brackets is the same thing as q1, q2 all of them bar, that is because they are operators, minus q2, q1, and everything is equal to 0. So if you take this minus q2, q1 to the other side, you see that q1 times q2 is equal to q2 times q1. It is just like saying 2 times 3 is equal to 3 times 2, and this is what we call commutative law from the elementary mathematics we know. So the requirement we have just seen, that the two operators must be commuting, that is, they must obey the commutative law. The operator is very important one in quantum mechanics. If this law of commutativity is not obeyed, definitely the result will not be observable, as we have explained. So what it means is that we can simultaneously measure the observables represented with these two operators if they obey the law of commutativity. But if the law of commutativity is not obeyed, you cannot simultaneously measure the two operators at the same time. For instance, if you can remember, according to Heisenberg uncertainty principle, it says whenever you want to measure the position of a particle and its momentum simultaneously, there must be an error. And that error is delta x in terms of position, delta p in terms of momentum. And the Heisenberg uncertainty principle says the product of the two is always greater than or equal to h over 2. And what this is saying is that in this Heisenberg uncertainty principle, actually the law of commutativity is not obeyed, and that is why these errors exist in position and the momentum respectively. So the next thing is the fourth postulate, postulate number 4 of quantum mechanics, and it is talking about eigenvalues. What are eigenvalues? These eigenvalues, they are just like set of random constants, which are always a scalar quantity, and of course they are associated with some linear equations. In most cases, the eigenvalues are obtained from matrices when 3, 4, 5 equations are expressed in form of matrix. So the eigenvalues are those set of constants which are associated with the equations transformed into the matrices. So the fourth postulate is saying the possible values of these eigenvalues, which can be measured, of an observable whose operator is A cap or A, can give the eigenvalues AI from this equation. Supposing this is my operator and these are the eigenvalues. So they are saying whenever you have that operator A multiplied by this function psi is equal to AI, where A is small letter and it is the eigenvalues, times the same the same function psi, which means it is from these operators that our constant eigenvalues should be obtained if you use this linear equation. And these eigenvalues, they are a complete set of n independent or time independent functions. They don't depend on time. We go to postulate number 5, that is fifth postulate of quantum mechanics. And what this postulate is saying is that the time development of quantum system, that is, development simply means evolution, changing of something with respect to time. So the time development of quantum system, they can be described by the evolution of the state function, and you know the function is represented by that constant psi, by the independent or time dependent Schrödinger equation. If you want to describe the time evolution or time development of any quantum system, you can use this time dependent Schrödinger equation. As you can see here in the bracket, I have R and T, where T is the time, and here also the T exists. So this is our time dependent Schrödinger equation, and it can be used to explain the time development, that is the changes in the values of observables when time changes, where this H is called the Hamiltonian operator of the system, and it is independent of time. That is, it is fixed. As time changes, it doesn't change. We go to the quantum postulates number 6, and what it says is that if a system is described by eigenfunction psi and of an operator E, then the value measured for the observable operator corresponding to this operator A will always be the eigenvalue A subscript I, which can be calculated if you use this eigenvalue equation. It is just similar to a postulate number 4, because this is my operator and these are the eigenvalues, and they are connected using this linear equation. So therefore, as I've already defined eigenvalues as set of what? Constants, which are always obtained from series of linear equations. So from this linear equation, if you have your operator capital A cap, you can always get the corresponding eigenvalue, those constant, for different unknowns. The last postulate of quantum mechanics is the postulate number 7, and what it is saying is that if a system is described by a wave function psi, which is not an eigenfunction of operator A cap, then the distribution of measured values will be obtained, and the average value of the observable property is given by the expectation value integral. This equation is what they call expectation value integral, where A is the expected value from this operator A cap, and here we are integrating the function with respect to the operator and the function with respect to the time constant. All over the function integrating another function with respect to time constant. Here you can see on the denominator we don't have the operator. So these values, which are called expectation values, they can be obtained if you solve this integral equation. So these are the 7 postulates of quantum mechanics. As we have already explained in our previous lecture, the quantum mechanics actually deals with microscopic states. That is something that is of insignificant size, that is not easy for clear or a visual observation. So the most important thing for you here is to follow this lecture again and again until you get the information that is being conveyed. And in case you come across any problem that you cannot solve, you are always welcome for further explanations. So after seeing the 7 postulates of quantum mechanics, the next thing is we are going to study the line spectra. This is what we already learned from our fundamentals of classical physics. We know that in any atom we have what we call energy levels, and we call it energy level ladder, because you have energy level E1, E2, E3, depending on how that shell, the distance of that shell from the nucleus. The one that is closest to the nucleus is the one that has least energy. The next one to it has a value of energy better than that. As you go further away from the nucleus, the energy level is increasing. And we have seen that whenever a radiation is directed to an atom, there is possibility that the electrons in their ground state shells, they can absorb that energy, and they can be energetic enough to now jump from that energy level to the higher energy level, which we call the excitation state. And we know they don't stay there forever. They will release that energy and go back to their ground state level. And here is the formula that is given us the difference, the energy between one level and the next. Energy E2 minus E1 is equal to HF, where H is the Planck's constant and F is the frequency of the radiation. You can substitute this F by C over lambda. And this Planck's constant is having a value, approximate value of 6.6 times 10 to the power minus 4 joule second. And this energy is always measured in electron volts. If you want to change from electron volt to joule, you multiply it by the charge of electron, which is 1.6 times 10 to the power minus 19. And as we have seen from here, this is the ladder we talked about, different energy levels and different amount of energy for the electrons in those shells. Another phenomenon which is very much relevant to quantum physics is photoelectric observation. We have learned from the basic physics that whenever a photon, that is light energy, is directed to surface of some materials, generally metals, if they absorb the energy from that photon, the light energy with high frequency, there is every tendency that electrons in that metal can absorb the energy and be able to escape from the surface of that metal, and that is what we call the photoelectric effect. And the incident photon, that is the light energy, must have some threshold frequency. If the frequency didn't reach that threshold value, the energy will not be enough for the electrons to escape. And the maximum energy Ke or Ek of the electron is independent of the light intensity. That is to say, the energy required by each electron to escape from the surface of any metal is independent of the intensity of radiation. And that minimum energy or that maximum energy is what we call the work function of that metal. The moment the energy reaches that, the electron can escape. And if it is below that, no escape or no release of photoelectrons. And in the process, the photoelectric current is produced, which is directly proportional to the intensity of the light. The more the intensity, that is the more the coming of the energy, light energy, the more the electrons that will be released, and therefore the photoelectric current will also increase, because it is the movement of charges that gives birth to what? Creation of current. Now, the energy of the incident photon in this photoelectric emission, E is equal to HF as I have shown in that formula, and the energy can do two things. Part of the energy will be used for ejecting the electrons, that is, it will use what we call the work function, the minimum energy required for electron to escape. The remaining energy should now be the kinetic energy for the ejected photons. Look at this diagram. Let us assume this is a potential well from where we want to eject this electron. This radiation that is coming in, it must have a minimum energy that is enough to take this electron from the potential well to the surface of the metal, and that energy is what we call the work function. So if the total energy from the incident radiation, which is HF, give us value up to this, it means it will be divided into two. The energy from here to here will now serve as the ejecting energy, which is the work function. The remaining from here to the peak should now be the kinetic energy of the ejected electron, which will enable the electrons to start moving away from the surface from which they are ejected. So this formula HF, total energy, composed of two components: the work function for the ejection of the electron and the kinetic energy for the electron to be able to move away from the surface from which it is ejected. Now we have what we call the photon flux, and this photon flux has to do with the total amount of energy obtained from the light energy incidenting on that metal. If you want to calculate the number of quanta of the radiation that is being emitted by the light source, let us assume you have a light source which is 100 watt lamp, and we assume it is a green light, therefore the wavelength is equal to this. So the total energy, as we have seen, E is equal to HF and F is equal to C over lambda, as we know. So we can now say this is the total energy. How? Go and get your a Planck's constant, 6.6 times 10 raised to the power minus 34, multiplied by C, which is 3.0 times 10 raised to the power 8, divided by the wavelength, which is 6 times 10 raised to the power minus 7. If you do that correctly, you are going to get this as the total energy. So if you want to get the number of quanta, all you need to do is now to say, okay, what is the rate of radiation of energy by the lamp? That is 100 watts, which is 100 joule per second, all over the total energy of the photon, which is 3.3 times 10 to the power minus 19. And if you do that, it will give you a total of 3 times 10 to the power 20 quanta per second. That is different packages of second up to 3 times 10 to the power 20 in 1 second, because we already know from our classical physics that the energy released by source of light like sun is not in continuous form, but it is in different packages, and each package we call it a photon. Also in elements are divided into two. We have what we call stable elements, and we have what we call unstable elements. And the unstable elements, they are called radioactive elements. So the energy that is released in the process of radioactivity is also not complete, single batch, but it is in different packages, and each package is what we call the quanta. Now the next thing we do is the building of a nuclei, that is to revise the presence of particles inside the nucleus of an atom. And we know that from the basic chemistry that there is discrete energy level in each nucleus, as we have just seen, and there is what we call fermions. And what is this, or what are these fermions? They are the particles that can never share the same quantum states. They obey what we call the Pauli exclusion principle. You can never get two particles that have exactly the same quantum state. That is fundamental quantum number, azimuthal quantum number, spin quantum number. All the 3 or 4, they can never be the same for these two particles. So those particles that will never allow themselves to have the same quantum state in all those 4 quantum numbers, they are called the fermions. For instance, if you get a proton and a neutron, they are both fermions. You can never get 2 protons that have all the 4 quantum numbers the same. And also you can never get 2 neutrons that have all the 4 quantum numbers the same. But you can have proton and the neutron sharing the same quantum number because they are not the same particle. Proton is a particle different from neutron, so they can have all their 4 quantum numbers the same. But you can never have 2 protons or 2 neutrons having the same quantum numbers. And that is what tends to keep their numbers in nuclei roughly equal. In most of the atoms, you find that the number of proton is equal to number of neutron. Let me take element number 5 for instance. Element number 5 is boron, and you know boron have how many protons? They are 5, and the neutrons are also 5. If you take sodium number 11, it has 11 this time around they are different, 11 protons, 12 neutron, and here they said roughly equal, not exactly equal. So those atoms that have almost equal or exactly equal, they are so because they are a combination of protons and neutrons which can have all the 4 quantum numbers the same. But if you get more massive nuclei, larger atoms, you find that the protons repelling each other have progressively more neutrons than the proton. For instance, if you take the ion number 56, you find that it has 30 neutrons and 26 protons, difference of 4. If you take lead, which has mass of 206, it has 124 neutrons but only 82 protons. So finally, we look at what is responsible for stability of any system. For instance, if you look at the gravitational forces, they are the ones responsible for keeping the solar system together. You know, the solar system, we have number of planets that are revolving around the sun continuously. So the energy that is responsible for keeping them together is gravitational forces. And also the electrical forces, it is the one that is responsible for holding components of atom together. It is the one that holds proton, neutrons and electrons together. It takes this energy if you want to pull them apart. That is why we have what we call ionization energy. Whenever you want to remove an electron from any atom or to separate protons from the neutrons in the nucleus, you have to apply an energy which is going to counter this electrical force that is keeping them together. And in each of them, the gravitational system and electrical system, you find that the energy of the bound system, the one that holds them together, is always less than the energy of individuals when they are separated. Why the difference? Because whenever you apply that energy to pull them together, it's like you are extracting some energy out of them. That is, you are overpowering part of their energy by that binding energy. And in the process of dividing them, you have to do some work for you to be able to separate them, as you did a work for you to put them together. And the energy of a bound nucleus, where we have our protons and the neutrons bounded together, is always less than the energy of the individual neutrons and protons if they are separate. And that energy is the binding energy, and it is responsible for what we call the mass defects. That is, the products, mass of the product when they are binded together is always less than mass of the reactant when the protons and the neutrons are separate from one another. And according to Einstein, he said the energy is always given by E equal to mc square, where m is our mass defect and our c is the speed of light, 3.0 times 10 raised to power 8. So ladies and gentlemen, as you can see, actually this course needs some concentration because it is dealing with some abstract aspects of physics. So I advise you, as usual, to watch it over and over again. Whenever you encounter any problem in the process of understanding, try to contact me so that we can discuss further for clearer explanation. Thank you very much. Till we meet in our next lecture.